Yo, 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 yo. Welcome. Today we're coding for fun. We're making a OS with the end goal of being able to post in my Twitch chat from my own operating system. So last stream we ran through the OS dev wiki bare bones setup. And let's see if we can find it. So this was written for C, and where it got us was to the point where we could write to the terminal in QEMU virtual machine for i686. And I wanted to see off screen how hard it would be to port this to Rust. And I was worried that there'd be a lot of compiler fiddling and building and stuff that wasn't really fun to watch, so I did it off screen. And we're at the point now where it works in Rust pretty well. So if I run cargo build and we check out my main, I have ported basically all of these functions from the terminal, from the C kernel that right to the terminal. I've ported those into a Rust struct that I initialized from a Rust function kernel main, exported as a C function. So this is the same thing where in their kernel main, they initialize the terminal and they wrote a string. Here I create my struct and I write to it. And all of these are basically one-to-one. So here we see this terminal buffer is a uint16 cast of this. We have this here. We loop over our width height and we initialize to 0. We do the same thing here. Yeah, and that works pretty well. So if I cargo build and then run QEMU, it says hey, we did it, a Rust kernel, so we're printing to the screen, easy peasy. And just to prove that this is doing what we expect, I can write something else. Hi, stream from Rust. And I build this. I can run that same kernel and it says hi, stream from Rust. Nice. So we're here, we've got a kernel in Rust. So if we look at what needed to be done there, let's just take a quick little peek. So the big thing is you need to define your own Rust target. So Rust has a bunch of built-in targets that x86-64 Linux, x86-64 Windows, i686 Windows, etc., etc. But what we're building is we're building a bare metal target. So we have to specify this special target here. And this just came from a couple of resources online. One was this getting started on building an OS in Rust blog, and as well as this i686 target definition that I found on Stack Overflow. And so basically, I think if I understand correctly, there's this data layout that specifies what the different types are. So there's a bunch of 32s in here, which I assume means 32 bits. I don't really know exactly what this is, but this is copy pasted from the Rust x86 version, I think. Here we say hey, when you're talking to LLVM, tell us that you're an i686, but you don't know what operating system, which is true. That's what we are. We're an x86 processor, little Indian, 32-bit pointers. And then the big thing here is I specified my linker to be the cross-compiled linker that we made last time. And in our link arguments that we pass all the time, we just say hey, use our linker script. Right, easy peasy. So when you're making an executable, don't make a normal elf. Use the linker script, and then that will set things up. So in our main function, we have our all of our initialization set up in assembly, copy pasted from the OS dev getting started. And so this defines the start function, which is expected by the linker. And so it's how do we get this into our Rust build? And all I did was I just said, hey, take that file and drop it into global assembly in this file. So we will now, when this main object is emitted, there will be the assembled version of this assembly just embedded right in it. I had to implement memset because some of the Rust embedded functions expect their memset to exist, and so all I did was just like iterate over the array, set all of the values to what you passed in. You have to set up like a panic handler, because Rust, when like something crashes, you might type like panic, oh no, and that has to go somewhere. So what ends up happening is it calls this and we never return. Then this is all the ports of the VGA stuff. Yeah, so nothing too crazy. And the other thing we have to do is we can get in like the core library. So I think I used this somewhere. Let's see. This might actually compile without core. Oh no, I needed core for global ASM and panic. So you can also configure in nightly builds. You can say like, hey, you guys haven't provided me the core library. Could you please give me I have the sources for them though. Could you just like compile them for me for my target? So easy peasy, all that's built in. And so now I've got that working. And what I think the next step here probably is it'd be really sick if I could get like the standard library collections from Rust. So if I look at like vec, it'd be really cool if I could get like a growable vector and this hash map. And it turns out that all I need to get these to work is they're actually defined in this alloc crate, which doesn't have a ton of stuff in it. And we get a lot of stuff for free here. So we get like copy on write, we get vectors, we get the big thing here that I want is we get hash do we get hash maps here? B tree map, binary heap, B tree set. Do I get like alloc? Do I get hash map? No, this is only an SCD, but binary B tree map, which is very similar, we get that. So it would be nice to have these like higher level types that we can use in our kernel. So today's goal is to get memory management working. And I thought that this would be like not too hard. But doing some Googling, it turns out that let's see, how do I say this? The memory allocators, how do I say this? Memory allocators work on pages. So if I say, give me, here, let's draw this out. Open up Paint. And if I'm saying like, here is my RAM, like this. So this is like, okay, how do I, let's start from scratch. So here's the CPU over here, CPU, and he has some like lines going out. And when he wants to access memory, he goes to this like memory controller, and this gets mapped to like this physical stick of RAM. So if I have, let's delete this, and we're gonna have like our little sticks of RAM. Here are the pins on them, and then I think they have like this little like notch on them, so you know where to put them. And we might have like two of the like multiple of these in my computer. I think I have two. And so this guy has like lines that go to here, right? Like womp 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 womp, and this is like heavily oversimplified. And I'll maybe let's put the disclaimer on that I guess frequently. So I think this is my mental model, but we may find out later that my mental model is wrong. But what else this memory controller does is if you look at our initial example, when we write to the VGA buffer, we're actually just writing to like an address, B8000. And so what this actually does is here's like my like VGA adapter. And he actually is coming over here, and he's got like some slices of memory here. So that's part one, is that not all of my memory is actually memory. right? There's memory mapped IO. And then the other part is, say from my CPU, I'm like, give me a gig of memory. I'm like, I just want, like, allocate me a gig. So if each of my sticks is 1 gig, I might actually not have that room contiguously. So let's say that, so these lines, let's say that these are just like, you can just like index them. So if you were to take like binary numbers, you could say like, this is number 0, 1, 0, 1. And that would go to like a specific point on these blocks of memory. And so if we like draw out our memory line like this, let's just, whoop, come on, lower. Whoop. I guess I can zoom out, bring it down, and zoom back in. So if I like have allocated like this and this, and I want, or let's say like this, and I want something that's like maybe this big, that doesn't fit anywhere, because we like fragmented memory. But if we like took this and this, we could like put these together to go down here. And so my understanding is that that's why we work in pages, is because it like allows us to shuffle things around. And it also allows us to like, if this is all the RAM we have, we could actually allocate like all of this, but not. And if we like access here, we'll be like, okay, we'll pull like some memory from over here. And then we access here and we're like, okay, we'll pull some memory from here. And it won't be until we accessed every single part of this memory and then ran out, that'd be like, oh no. And this also lets us do stuff like if we run out of pages in physical RAM, we can actually just like take them out of RAM and stick them on disk, right? Like swapping. So my initial thought was maybe you can like skip all of that. I think for sure you need to handle this, right? But maybe you don't have to handle paging if we just say that all addresses map directly to physical memory. But there are like extra protections that we might get from implementing pages. So I was looking at like OS Dev Wiki. I was looking at the wiki and was looking at, what was it called? Paging. And it looks like this concept of like paging is built pretty deeply into the CPU. Specifically, like the CPU expects us to have pages, and we can like upload our page table to the CPU, and then we get nice things like, you know, when you like dereference 0, if I write like a shitty little C program, and in it I just like return star null. Can I just do voids? Let's cast this to like a char star 0. So here I segfault, and like, what does that mean? And so if I understand what I've been reading correctly, it means that the CPU goes, hey, you haven't asked for that address. You're not allowed to access that in this process. And so I'm gonna like, because I know what pieces of physical RAM I've allocated for you, and you're trying to ask for something that you don't have, I'm gonna like go like, oh no, panic, segfault, and that allows like some nice protections. So I think I'm gonna try doing it this way, setting up a page table, uploading it to the CPU, seeing where that goes, and let's just kind of see where that takes us. So I was also reading and experimenting a little bit. So if I, let's see, how do I say this? If I go into my main, is this the wrong window? Yeah, here we go. And I want to start like using the alloc crate, I can do extern crate alloc. And I can I think it's cargo build. config. Yeah, here we go. I can like say, please compile the alloc crate for me as well, right? And now if I build, it's going to say like, hey, you have to set up a global memory allocator. And so I was like looking at how to do that, and it looks like you can just create an allocator. So if I look at alloc in Rust, where do I find like allocator? I was seeing somewhere that like you can assign, you just like create this allocator trait and you assign it to the global alloc. Global. Okay, not sure. But you can basically like assign this global allocator. And I think I can use a normal, like just like an existing malloc implementation, assuming that I have implemented paging. So if I wanted to like use JMalloc from Rust, this is like something that we already exists, right? You can just use this JE mallocator, and this implements the global alloc trait, blah blah. And oh yeah, here we go. Using JE malloc as a backend, so this is like definitely possible. And I was also reading that in the OS Dev wiki for allocators, I was reading that you can just use JE malloc directly, but I just have to implement these like alloc page and free page. So the existing allocators know about the concept of pages, and all I need to do is like give them pages, right? Easy. So we can say like JE malloc just requires us to provide and free pages when asked for them, which means that our to-do, it involves implement paging for i686, hook up paging to JMalloc, right? In Rust kernel. Okay, so hopefully this is enough context to get going. And yeah, I think let's just get started. So I think what I read is the multiboot spec provides us with our valid memory ranges. So it will remove things that aren't like VJ and stuff. So multiboot. So the first thing we need to do is like read multiboot memory info, and then from there we can use that to start like setting up what are our valid memory ranges, etc. And I think this is like just an easy initial win. So here, if we go and look up multiboot, we're using multiboot 1, and I was reading here that we've set please give us memory. So if I look at this boot script, we do say, hey, could you provide us a memory map? And which is flags 0 is set. What about flags 1? Boot device? This doesn't line up with these docs. That's kind of fun. Well, at the very least, the EBX register contains the physical address of a multi information data structure. So let's start with that and just see if we can read something that looks maybe sane out of this. So that requires some assembly to pull some data out of that register. And it also probably requires some like knowledge of this data layout, and also requires how to say this, knowledge of like how to get info from our assembly into our kernel main. And so I was reading about x86 calling conventions. And there's like a bunch, right? There's no real like definition of what's going to happen, right? I think the call function in x86 assembly, I'm not sure what it does. I'm not sure if it like if it does any like explicit cleanup setup or anything. But if we assume that it doesn't, then we have to like set up our calling convention. Like we have to like put our registers in the correct state. So right, if your function expects that you're like going to pass a parameter in like the first register, that what it defines as the first register, you need to like put that value there first. And functions might like kill or clean up registers. They might like clobber them if they feel like it. Anyways, there's like a bunch of like different sets of rules. And I'm pretty sure this like wasn't really clear to me. But I think that GCC, and hopefully therefore my Rust implementation, uses the syscall setup, which is basically just saying push arguments on the stack. So we have this like stack pointer. Let's just go down some more. Let's just make this. Oops. No. Okay. We'll just make this page really big. Resize the image, please. And we have like our stack, right? We'll just call this like memory. This is how people draw it. And we have this like register ESP, which I don't know what the E is, but we'll call this the stack pointer. And this is going to point to like some memory. So if I have like 0, 0, 0, 0 here and like something big up here, like 4096, this might be pointing to like here. And what I want to do is, if this is where we're starting before we call main, I basically want to like push in my arguments beforehand. So if I want to call like main with like an input parameter 1, I would like push 1, put 1 in this location memory and move this up here. And I think that's essentially what we are doing here. Let's see. Because if the multiboot spec says that in EBX, this is going to return the 32-bit physical address of multiboot information. So if I just push that value onto the stack, I should get a pointer to the multiboot, I think. Which means that I should be able to read these values if I want. So that's what I want to take a look at. See if that works. Which means in main, we're going to need like a structure for multiboot info. And we want to say, hey, Rust, please don't like rearrange stuff for optimizations, because like I have this very specific way that I want to lay this out in memory. And so that's what this like repc basically means, like please follow some rules for how you're going to define stuff. And this like pact says like please don't like it might be more efficient sometimes to like put space between items in your struct for like memory alignment reasons. And this is basically saying like no, please don't do that. Just like put the stuff as soon as you can. No padding, please. And so here I should be able to say flags is a U32, and mem lower should be a U32, and mem upper should be a U32. There'll be some like other stuff here, but if I don't want to look at it, I don't really care. Right? Yeah. So let's like just see if we can read that. And so what I think should work is if I go to boot.s, if I move, how do I say this? So this is AT&T syntax. So this is going left to right. Right. I'm moving the stack into ESP. So here I should be able to say like, push EBX, I think. Let's look this up. x86 SM cheat sheet. Yeah, let's see this. No, I don't want to go to Amazon. I just want like Okay, so push. Add to the top of the stack. Mem minus RSP equals source. And okay, let's see if this compiles. Okay, so I have to undo the like allocator stuff. So here I go back to main, remove this alloc crate, and go back to cargo build. What is this config? And remove alloc crate because this was just for demo purposes. Okay, so this builds, and now if I what I probably want to do now is I want to print what I get in here. So here I'm going to get a U32, which is the multi-boot header. Can I push just like a number to the stack? x86 push number to stack. Hello. Or x86 push immediate value to stack. Why is my internet so slow? Come on. I need those bits, baby. Okay. That's up to the assembler. Okay, so let's try. So if I understand correctly, if I push let's try pushing like a character, because I don't have any way to turn numbers into strings right now. So if I look up the ASCII character, if I'm correct about the calling convention, if I push in, is this hex? Dude, what a stupid table. Tell me what units you're in. Here we go. So I want capital A in hex is 0x41. Let's see if this compiles. And if I go to main now and I say read this as a U8, I wonder if this will work. And I can just write. Do I have like a write car function? I think I must have put car. And so if I understand what I've done correctly, I've pushed hex 65 to my stack, called my kernel main, which means that this should now be the first thing on the stack, and if I put that character here, I should see an A on the screen. So let's run this. W. That's close. This might be due to, let's see this again. So I was gonna say this might be due to the fact that I'm not allowed to pass a U8 like that. So let's see. Still W. Okay. So there's something I don't understand here. Let's see. So if I increment this by 1, does my letter increase? Okay, it definitely is something different. Let's just, I'm not sure if I'm allowed to push immediate values, so I can say move 0x42 into EAX and then push EAX and see if that behaves any differently. No. Okay. Interesting. So, what do I make of that? What do I make of that? That means that either I'm not printing correctly, or this isn't working. So let's start with this. If I push 42 here, just say I'm gonna write 42 now, I get a B like I expect, which means that my argument passing is not behaving as I expect. So here, let's try this again. Oh, wait. Oh, it's still... Oops, this needs to be multiboot header. So cargo build, run it, get nothing. Okay, so what if Rust is deciding that it wants to use the fast call API, right? So I think I saw there's fast call, which has not been standardized, but I think that it like puts some of the arguments in registers. Let's see if in Rust I can set calling convention for function. This will give us a little bit of extra info. Wow. They're still experimenting with different divides. Rust can do it. Okay. So I think that if I do an extern C though, like I am here, Rust extern C calling convention. That has to be well defined. Calling convention. C calling convention, as discussed below in here. Oh, okay. So what did I think I was using? I thought I was using syscall. Okay, so how do I know what the C calling convention here is? They're saying I can set my calling convention as C. So most APIs in this list are self-explanatory. Maybe to you. What about to me? I don't know what's going on. Accept all cookies? Yeah, sorry. You're right. I shouldn't do that. But oops. Repr C. So what am I? C calling convention. x86. Okay. Here's some PDF. Push EBP, move EBP, ESP. Okay. What does the caller do? I guess I could actually look at the disassembly for this and just see what it's doing. That sounds kind of fun. So target kernel. Oops, it's objump-d, I think. And let's look for kernel main. Okay. So he's pulling some stuff for the stack. Let's remove. Oh, I have to keep that. Dang. Okay. Kernel main. What's he doing? So he's subtracting 20 from the stack pointer. He's calling. Probably this is like the. I'm actually not sure. So this is the put car function. So he's calling this. So he moves EX 4 bytes into ESP. There's no like push call here. Oh, what's this going on? He's doing some adding, blah blah blah. Okay, I'm not gaining any info from this. I thought that this would help me, but it's not. So where does he tell? Oh. Save value of EBP, return address. Did I miss a push? Push 1, 2, 3. If this is call 1, 2, 3, he calls 1, 2, 3. Save old call frame, initialize new call frame, sure. I think this is going right to left, so he's saying, hey, put what EBP was onto the stack. put ESP into EBP. Push call arguments in reverse, right to left. The enter instruction can also do something similar. Why? Oh, I see. So I could have moved things into here directly, but doing a push should be the same. Oh, okay. So the first thing it does is, why are these working on EBP instead of ESP? Because at the beginning of this function, we put the EBP into the stack pointer. So if my EBP is uninitialized here, it won't work. So if I say in here, EBP as well, maybe he'll like that better. Which I can test with QEMU. Nothing. Nada. Initialize new call frame. I feel like I'm missing something. I feel like I'm missing something. It would be nice if I could pop open the debugger and just look. So this is doing the same thing where he's like putting the value of EBX, which is the old stack, onto the stack, so that at the end probably he can like pop it off. Oi oi oi. How confusing. How confusing. Okay. How can we test? It'd be nice if we get like GDB set up. So I think, if I remember correctly, QEMU has like a way to get a debugger running remotely. So QEMU GDB server. Oh, but it's gonna require debug info that might not exist because I'm like linking manually. Okay, let's punch in a few arguments here. We'll call these integers. Let's support writing integers as ASCII so that we can print them to our screen so that we can actually like debug this a little bit. Oopsies. So let's just make a function put in, and let's for now say that this has to be a U8 because I don't want to deal with dealing with digits. And then I can just call put char C plus whatever the starting value of like the numbers are. Oh, I actually do have to deal with this. Okay, so we'll make this an I32, and we need to turn this like number into like a base 10 number, split some digits. Implement print number. Okay, so we'll make this mutable, and we'll say, well, C. So we'll say we'll loop we'll divide C by 10, and we'll make our digit is the remainder of the number divided by 10. So if I have like 20, I'm going to divide that by 10, I'm going to get 0. I'm going to divide it by 10, I'm going to get 2. Okay. If C is 0, we're done. And this is going to give me like digits right to left. So every time I iterate through this loop, I'm going to get like the lowest digit, which is actually kind of problematic because I print left to right. So I actually want to start with the highest digit, which means that I need to find the highest digit first. So I probably need to find what value of C produces 0. And then work backwards from there. So let mut C or num digits equals 0. Or we'll start with 1, right? Because it's always going to be 1 digit. And while we're going to increment this by 1 if we can divide, if we get a non-zero value for the division by 10. So we'll say C divided by 10 times num digits. If this is 0, we break. Otherwise, we add 1. Right? So now we have our number of digits. And for digit in 0 to num digits, we want to do this backwards actually. Do I want inclusive range here? So if num digits was 1, I still want to do 1. So we go let digit equals C divided by 10 divided num digits minus 1. Let's think. I want the second last digits. So if this is 1, then this will give me 0, which means I need to do 1 to num digits. 2 to num digits? I can't divide by 0. Am I going crazy? Probably. What am I missing? So if I want to do the tens place, then this should be 1. If I want to do the hundreds place, this should be 10. Sorry, if I want to do the tens place, I should be sorry. If I have like 100, or let's say like 120, and I want to print digit 2. The digit 2. I would do 120 divided by 10 mod 10, right? Which means that I know that this is 3 digits. Let's just double check that. So here, if I have C divided by 10 divided by 1, it's not 0 because that would give me 12. So I'd increment it. Then I'd do C divided by 10 divided by 2. Oh, I'm being stupid. This should be a power. So is there like a pow function in Rust? Is this in the standard library? I think no. Let's try it. So here, pow num digits. Right, so here I would go, if my number is 0, I break immediately. If my number is 1, I break immediately, because c over 10 is going to be 0. If it's 11, I do 1 iteration, then break num digits 2. Okay, so I'm pretty sure this is right. So now here I have num digits. And so I want to go c divided by 10 to the power of num digits minus 1. Which means that if I get 10 to the power of 0, I'm going to get 1, so this is fine. So here I'm starting at, this is a 3-digit number, so I'm going to start at 3. So I'm going to do 120 divided by 100, which is going to be 1. So I actually want to do 120 mod 100. That gives me 20. What is J.E. Malik? Okay, so wow, you're behind. So, or I'm behind, who knows? So how do I explain this? In C, let's make a little test C program. Include string. So if I make like a little function and I want to like in a function, okay, I don't really know how low level you've gone, but if I want to like allocate some memory, I'll call like Malik 4 or something. Let's just double check. Yeah, so this is the size in bytes. So if I want to like get an integer, I can say like int x, pointer to x is Malik 4. And this will give me like 4 bytes that won't go away. So say I wanted to like it's a bad example. Say I wanted to return like a string from a function, so I would have like my function, and if I were to just like return 1 2 3 4 here, this would like if I like allocated an array here and this was 1 2 3 4 and I tried to like return this, I think it's char x4, and I want to like return x, this is like invalid because what I'm returning is like memory that's in this function that will be gone when the function ends. So what you would do in C is you would like say, hey, operating system, could you like give me some memory instead? So you'd say like, here's a pointer to something, and I'd say Malik, my 4 bytes to say 1 2 3 4, and then I'd say star x. I don't really remember how to initialize this sanely. But you could do like this, where you like get some memory, you set the values in it, and then you can return this, and this is like now no longer going to go away. So I have like car star x equals my function, and then at the end I have to say like free x to say like, okay, I'm done with this now, please go away. And what actually happens when you do this is you call into this like library called libc, and he calls into the OS, he goes like into the kernel and he says like, hey kernel, could you give me some memory please? And I'm not really, I think the kernel handles large chunks of memory and libc handles like small chunks. So he goes into the kernel, he goes like, hey, I need some RAM please. And the kernel goes like, here's like 4 megs of RAM. And he goes like, oh, I only needed like 4 bytes. Let me like quickly grab those and I'll like remember this for later. And so the idea of like something like J.E. Malik is, you could argue that like if you're allocating memory a lot, which most programs do, right? Like any like if you're writing in like JavaScript, you're allocating memory all the time. Basically like every object you have is like heap allocated. You could argue that you want to go faster. And so you could argue that like the default system implementation of like get me some memory might not be fast enough. And so there's like alternative implementations like J.E. Malik. And that actually gets us a little nice freebie here where I'm like, well, in my OS, I don't have libc because libc is implemented directly for Linux or for Windows. And so I'm like, oh, I'll just grab this other implementation of like managing pages and turning them into pointers, and I can use that in my kernel and then just implement like the backend for that, which is like get me some pages. So JMalc is just like someone's implementation of give me some RAM, please, essentially. Yeah, so that's what we're going for. Cool, gracias. No problem. Okay. Going back to trying to print a number. This should be trivial, but God, my brain is not there. Okay, so if I say I want the 2 here, so I'll be at digit, so this is 0, this is 1, 2, 3, and if I'm at like digit 3, I want to print this 1, so I will divide by 10 to the 2, which is 100. Oh, and I'll have the 1 left. Okay, so then if I'm on digit, so this is on digit 2, I will divide by 10 to the 1, and I can mod 10. Okay, cool. And then I can just self put char digit plus, I need to convert this to ASCII, which here is just plus 0x30. And now we can test this by just in my main writing some numbers. 125. Oopsies. Cargo build. Build it. He didn't like that. Why not? Cannot convert either 2 to U8. Oh, I see. So here, this guy needs to be as U8. Oh, you're such a whiner. 123. This also needs to be explicitly typed as an integer. Okay, now if I run this, 111. Which is not what we wrote. We wrote 125. Great. What if I wrote like 555? Oopsies, let's build it first. So we build, and we run, and we do get 555. Okay, so we're close. 555 turns to 543. So it looks like we're just printing the first digit every time. Which is interesting. How do I fix this? Oh. Oops, this should be C, and this should be digit. I'm just using the last digit every time. Oopsies. Okay. There we go, 543. So I think I can write numbers now. 1, 2, 3, 7. Here we go. 9568. 9568. Okay, we're chilling. So we've accomplished something. We can like check that off, and we can like cheer. Hooray! We did it. So now what I should be able to do is I want to see what happens if I print arg and r. Well, let's just start with this. So that's not a number for some reason. Maybe because it's I haven't handled negatives. So if I say -1 to 3, yeah, that does some like wacky shit, which means that if C is less than 0, I put the negative sign myself, which is, I think I can just write I want a byte string dash sign, and then I can say C equals -C. And now I get -1, 2, 3, like I expect. Huzzah. And now let's try printing stuff. So now I can start pushing numbers onto the stack and see what I get. So if I push like 1, I get nothing. 1 through 4, 1 through 4. So these are definitely like changing what I get. Move 1, 2, 3 into EAX and then push EAX. Does this give me something interesting? No. So, first of all, why is that even capable of printing non-number characters? Right, because this should only result in a number between 0 and 10. Unless... Oh, oops. That negative sign needs to go in here. Okay, right, because I just broke all positive number printing, obviously. Okay. So now let's say... let's just put in, like, int max. Okay. Is that right? Calculator. 0xFF. 429, 4967. No. But that does look what, int to, or decimal to hex. That looks like a number I feel like I recognize. So that's 167. It's interesting to me that like I'm pushing to the stack and I'm getting like deterministically different numbers. But they're not what I expect. Right, like, that's 0. Also 0. Yeah, like, why? Oh, do you think this thinks that this is like a memory address? The ABI requires that the stack is 16-point aligned at the time of call instruction, blah, blah, blah. The stack was really 16-point aligned, and we pushed multiples of 16 points to the stack since then. Oh! Okay. So, here this is 4, 8, 12, 16. So now what if I punch in, like... This is odd. I've actually done no pushes to the stack since then. Yeah, I'm missing something. How can I test this better? Let's check out other x86 calling conventions, and maybe we're in one of those. Oh, C declaration is a calling convention for the C program language used by many C compilers for the x86 architecture. Subroutines arguments are passed on the stack. Integer values and memory addresses are returned in the EAX register. Floating point values, and blah, blah, blah. So I don't... This seems like pretty straightforward. Let's just try pushing EBP and moving ESP to EBP. Just as like a sanity check. And then let's move like 13H, or let's say like 0x30, or let's just do this one. 1, 2, 3 goes into EAX. push EAX because I'm not really sure if I have to do that. And it has to be 16-byte alliance. We'll push 4 times. And let's see if this is deterministic. This is related to this number in some way. Right? Okay, what if I punch in just full Fs, 2928, and then add 1 to EAX. Oh, I guess I should sub 1 from EAX. Yeah, I'm not seeing it. I'm not seeing it. I'm definitely missing something. Okay. So let's look at the OS Dev Wiki. Pass arguments to kernel. Okay. So calling conventions on the OS Dev Wiki. Here we go. Basics, as a rule of thumb, blah, blah, blah. Scratch registers, preserve registers, call list. Parameter registers, none. Return value, EX, EDX. So this is what I expected. So this is blah, blah, blah. i686 elf GCC. External references. Passing function arguments. This really does seem like this should be it. GCC x86 passes arguments on the stack. These arguments are pushed in reverse order from their order in the argument list. Furthermore, since the x86 protocol protected mode stack operates on 32-bit values, the values are always pushed as a 32-bit value. Even the actual value is less than a 32-bit value. Thus, for the function foo, the value of QUX, a 48 floating point value, is pushed as two 32-bit values. Okay. The calling function must push the argument values as described above. Let's call foo from an assembly program. You would do something like this. Okay. So accessing function arguments. So we like pull from them. So I guess it would be interesting if we could check somehow if we're getting what we expect. Hum. It's interesting that they're using EBP, not ESP. Because oh, do I have to? No, okay, so here all they're doing is they're pushing to the stack. Oi, oi, oi. Remove call arguments from the frame, modify subroutine result. Sure. Restore all call frame. Sure. So I'm confused because I'm seeing very clear effect. Like if I, first of all, I should only have one argument here for now. Like if I set this to 0. Oh, oops, nothing happens here. So if I do not, if I push 0, I see like a number, but it's just not the number I expect. And it's really weird that I see a change in behavior. So how can I debug this? I have so little info. Right, like it's very clear that this number is changing what happens here. 112.76288. 112.76288. Okay, that's interesting. So how come when I change like from 0 to like 1, I get different? If I change this to 10, I start to see like negative 112.726.288. That's a different number again. Yeah, I'm missing something. Let's read the... well, what we could do is we could scratch the Rust side of things, and we could try doing this in C only. Does that help me? It would like decouple the problem from Rust's ABI to C's ABI, but that means I'd have to implement the integer printing in C again, which I don't know if I want to do. Thinking. Interesting. It really seems like this isn't complex. So I wonder if there's like other things I can test here. Let's look at the disassembly again. I know I'm going in circles, but I'm scrounging for scraps here. Kernel main. Here's what we can do. We can return an int here. And we can see what happens. So here my kernel main takes 4 bytes back from the stack pointer and puts it in EAX. Right, so that's exactly what we expect, right? We expect that 4 bytes back from ESP, we end up with this. So I wonder if we can confirm this in some way. So maybe it's this push call isn't doing what I expect. So if I undo this, let's see if there's something happening with like terminal writer overwriting something. So now in kernel main, I should see, since I'm now doing like a variable assignment, I should see like a move of that value. Yeah, I pop it into EBX, and then if I return EBX now, return X. Let's see what I see here. Kernel main. So I pop into EBX. Where do I set here? Move ESP minus a bit into EAX. And if I print X, so I should see something like when we call this putInt function. Okay, yeah, so here we're putting EAX onto the stack pointer, which is our return value, which means that somewhere we pulled it from the stack onto EAX. So is there like a pop EAX somewhere? Here. I don't know if this goes like left to right or right to left, which is like annoying. Obj dump obj dump operation in order. Take a little peek. Obj dump disassembly Intel AT&T. Oh, I see. So I can say, let's emit ATT, maybe? So that's what I'm working with. And like, let's look at the AT&T syntax. So AT&T. Here. So source is before destination in AT&T. Okay. So if I look at the kernel main output, here I'm putting EX into the stack. Where do I get this? So we take 28, hex 28 from the stack. And we've moved hex 20 forward. So let's think about why that would be. We have 20 bytes of memory for our, or 020 for our 4 integers in the terminal writer, or more than that. Okay, so in our terminal writer that is sitting on the stack here, we have 4 bytes, 4 bytes, 1 byte, 4 bytes, assuming these are 32-bit ints, which is 4, 8, 12, 13, or like, is this 8 bytes like this? 8, 16 plus 5? No. Oi, oi, oi. Oh, but these are going to be padded probably. So if I repc pack this, just to make sure I understand, I should see a sub of 8, 16, which is 10. So I should see hex 15 if I build this. Cargo build, obj dump, kernel main. Still 20. Okay, so I don't understand. But that's okay. That's okay. I wonder if there's a way to... Let's think. Let's move the terminal writer stuff into a new function. Function print stuff, right? This way, this doesn't pollute my stack, and the kernel main function will be very straightforward. So I can say print stuff arg. Like this. And I can look at the disassembly again, and the kernel main should be much simpler. Nice. Nice. So here I say, hey, my stack's gonna have the same thing that it had on it. That's why I'm subtracting 8 bytes. So let's think about that. I thought that I was working with 4-byte integers, 32-bit. So why am I subtracting 2 here? I think I read something about like stack alignment. Okay, let's transform this so that it becomes a little clearer. I can see where the addition is happening. Okay. So I noticed that they're doing a odd add here. Can I like make these optimizations easier? What is this jump not equal here to down here? Oh, because there's panicking. Ugh. Okay. I do notice these $ values. I wonder if this is what I'm supposed to do. I wonder if I messed up my syntax. Oh my god. Oh, that was it. Okay, so this means that like I just spent all of that time struggling because my assembly is wrong. My assembly skills are not up to date. So now the question becomes, what the fuck does this $ mean? AT&T $. What do the $ percentage signs? This is not Intel text. This is also called gas text. This means immediates, which is what I was trying to do this whole time. This whole fucking time. But usually no prefix, blah, blah, blah. So what happens if I omit both? Memory reference, probably. So I was probably just saying like, hey, read this arbitrary memory value, and as I change it, I was getting different results, and it was just like reading from different points in memory. That's so fucked. Okay, I should have known. That's on me. I should have known that. So here we get argument from stack into kernel. Okay. God, that makes me feel so much fucking better. I thought I was losing my mind. So this is all right. Okay, so I can print numbers. I can put them into the kernel through arguments, which means now that if I say I'm going to get a pointer to a multiboot info as the input here. So I'll say its info is a pointer to multiboot info. Let's now print info flags. Okay. Okay, I need to dereference this, obviously, like this. And as I32. Could not dereference a raw pointer without writing unsafe because Rust is like, hey, pointers are dangerous. And I want to print this as a U32 actually, which is annoying. Probably. What is this? Yeah. Which means I should have a put. These shouldn't be called put. It should be put I32. Or put signed, and we'll put T. Is there like a traits for integers right now in like core? So in the core library, boy, let's look at like U8 primitive type and like what kind of traits do they have implemented. I want to know if they have like signed integer types or something. No, alright, whatever. Well, not that I'm aware of. That's okay. So we'll just call this put I32. And we'll have another one put U32. And we take all of this stuff except for like the int conversion. And we now just call self put U32 C as U32. So we've removed the negative. And now we just do this. And now hopefully that means that we can print we can just print this as a U32 now. So let's make sure that put I32 still works as expected. So we'll put like -123 and 456. And we'll test put U32 as well and put like 789. We now need to change all of these like I32s in here to U32. Oh. There's no new lines, but I see -1, 2, 3, 4, 5, 6, 7, 8, 9. Solid. So now we should be able to print what the flags we got from multiboot info are. So info flags. Right, I still have to dereference, and it's going to tell me that I need to put this in unsafe again. I don't know how I ended up without this. I must have put undo a few times without thinking about it. Nada. Why? 0. I should get something. Hello? Let's see if, like, there's something that's crashing my program. Yeah, so this is just never happening, which means that maybe this is an invalid pointer. Right, so let's see. This is U32. Oops, let's get rid of this away. So this is at memory address 10 is what I'm getting put in. Oh, I'm an idiot. I'm just still passing in 10 here. This needs to be EVX. And now I'm getting something that maybe I can dereference. So, info flags. What doesn't it like there? U32 cannot be referenced, right? Because this is a const multiboot info. Okay, that's a number. And let's print the lower and upper values, because and this should 639 is the lower and upper is hopefully some big number. Okay, so that's 129620 minus 639. 129620 minus 639 is not very much, right? I would expect that my QEMU RAM has more than that. What about like 531 in binary, which was I think the flags that that came out. Typical multi-boot flags. Must contain the 32-bit physical address. Oh, okay. So we can check. Let's check EAX contains the magic value. That will give us some confidence that we're doing something right. So, oopsies, didn't double that. So we'll call this multi-boot magic as a U32. And we'll put multi-boot magic here. And in our boot script, we push right to left, so this would be EAX. And let's see what this magic is in decimal. So here we just go Python. Oops, let's just quickly install Python 3 so that I can do some quick little hex to decimal conversion. Womp 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 womp. Okay. So 732.803.74. Okay, which I think is what we saw there. Right, so we have 732.803.074. 732.803.074. Okay, so we have confirmed multi-boot EAX argument. Multi-boot magic. And so the next thing we want to do is we want to make sure that this like struct layout is what we expect. So EAX must contain the magic value. EBX must contain the 32-bit physical address. Oh, but did I fuck up the EBX register in here? Oopsies. ESP. No, I didn't touch EBX anywhere. I just pushed it to the stack. So theoretically, this should be right. And let's see if we can, maybe let's see if we can figure out what flags are set. So somewhere I converted that to binary. Maybe that was, do I still have that open? No. That's okay. Oh, wait, no, okay. It's okay. So let's print the flags. And 591, so we'll say Python 3. Oops. Let's just add Python here because I'm going to be using it a lot. So we have Python open now, hopefully. And what was it? It was 531. Email 591. That's the flags we're getting from multiboot. I forgot again. No. 591. 591. Okay. So print. I think I can just say like %b 591. Ugh. Python format Boolean. Format binary, sorry. Into binary string. Yeah, it's fucking... Okay, maybe I have to put 0b format 501. Okay, so this is bits 0, 1, 2, 3, 4, 0, 1, 2, 3, 6, 9. So according to this, 0, 1, 2, 3, 6, 9. So I should get bootloader name. Oh, that's an interesting one. This will tell us for sure if we've got something saying. Okay. So this is boot device. Command line. And then we have these guys, mods count, mods adder. Sims is 28 to 40. Oh, you know what we can do? We can just add 64. Let's just do that. Instead of casting like this, let's say the info, we can say that like the bootloader name is info 6 plus 64. Right? Because that's what this is here. 64 bytes away. And I think I dereferenced this. And this is a U8 array, probably. And now let's just try writing that to the screen. So we can say terminal writer, put, was it write maybe? Yeah. So we say write, and let's just like take this as a slice. So bootloader name. Can I like create a slice from a pointer? Rust slice from pointer. Right, because I just want like from raw parts. Oh, but that's from stud. No. Does core slice have anything? Okay, ooh. Core slice from raw parts. Bootloader name, and we'll just say like, let's get like the first 4 bytes. And we'll write name slice like this. And we actually don't need this right now. Okay. we'll make this a const u8. What doesn't it like? Oh, I have to source the environments file to get my linker back. Okay, so that gave me nothing. But maybe this add is in units of the thing, so I have to do over 4. Oh, baby! Let's go! Okay, so this is like a really good sign. So that means that in our kernel, we are getting this like multi-boot header. Which means that the start and end values for our RAM were probably correct. So let's, did I lose the multi-boot thing? Oh, that's 6. Okay. So mem lower and mem upper. Let's see if those are documented. If bit 0 flag is set, then the mem fields are valid. Indicate the amount of lower and upper memories respectively in kilobytes. Lower memory starts at address 0 and upper management memory starts at 1 megabyte. The maximum value for lower memory is 640 kilobytes. The value returned for upper memory is maximally the address of the first upper memory hole minus 1 megabyte. Whoa. What is upper memory hole? The first upper memory hole minus 1 megabyte is not guaranteed to be this value. Lower memory address starts at 0, starts at 1 meg. Okay. So what does that mean? What about mmap length and mmap adder? I don't understand what this like mem upper means. Mem upper indicate the amount of lower and upper memory respectively in kilobytes. Upper memory starts at address 1 megabyte. So that's like where my kernel was loaded, right? When I make my linker script, if I look at linker script, we block off 1 megabyte. And so that's probably why this mem upper starts at 1 megabyte. So like if I look at my like text, I should be able to like find my own code at the beginning at here. So what is, so mem upper starts at address 1 megabyte. So multi-boot mem upper. Let's see if somebody else can help us figure out what this means. Because that is not clear to me at all. At all. From the get, this is what I want. So I want to get the available RAM from the grub2 multi-boot infrastructure. Simply put, you can't. No! These are obsolete fields? Fuck! Okay. Holds the size of the first contiguous... Oh, okay. This second part is important enough to deserve a further discussion. The memory itself can be accessed at the memory controller level as a continuous block. It is not continuous in the memory subsystem level. The memory subsystem creates holes in the contiguous address range assigned to memory either by simply not reclaiming specific subranges or by shifting blah, blah, blah. Historical evolution. Okay. Ah, okay. So I should use the mmap functions. Okay. Right. So this is some old shit. Right? And there are holes in memory. So instead of looking at this, we should say like, hey, what are the like available slots? Like what chunks of memory are available? And these mmap functions or this mmap list probably tells you which areas of RAM are usable. Haha. Yeah. Okay. So probably instead of recreating this from scratch, I could probably yoink the multiboot H header, convert this into like a Rust thing. which would allow me to like just use this code as expected. Okay. Okay. So what does this do? Yeah. Okay, so let's actually first, here we're going to add new lines to our printing, right? So that we can start logging like multiple things at a time. So here, we'll just say if the C is a new line, we increment the terminal row, and the terminal column is 0, right? Easy peasy, which means that now we can start logging multiple things in a row. So we'll say here we want to put char \n. And here, if we write this twice, we should now see QEMU. Okay, that's close. But I forgot to return here. QEMU. Okay, so we have new lines now. Great. And now that we have that, we can start. Let's start like trying to like print out each of the mmap structures. So first, let's try to grab this multiboot header. Which, oh, here we go, multiboot 1 header file. And we can just yoink this bad boy. Is there like a download raw? I'll just fucking copy paste it, that's fine. Okay. Right, okay, so here's the multiboot header. And now we need to convert this into something usable by Rust. So there's like this project, cbindgen. And let's add this to our to-do. So we're going to generate bindings for Rust for multiboot header. There's this project cbindgen that basically like lets us take, or is it just bindgen? One goes from C to Rust and one goes from Rust to C. Bindgen automatically generates Rust FFI bindings. So this will take like this C header file and just convert it into like Rust code that I can call directly, saving me a little bit of work. So I think that the bindgen docs say that I can use this directly from my build script. Maybe I'll just generate these manually. Bindgen binary Rust. I think there's a way to just call an executable. Bindgen CLI. Oh shit. And I remember some like bullshit NixOS stuff that makes this hard to use because this requires like libclang to be set or to exist. And the like environment variables that have to point to libclang, if I remember correctly, don't line up very well. So I think I have a project that I've actually worked on where I had to deal with this before. Let's hope that there's code uploaded to GitHub somewhere. Apex. No, there's not. Okay, so this is not on GitHub at the moment. Unfortunate. But let's see what bindgen can do. Bindgen. So if I go into kernel or source, bindgen multiboot.h. Yeah, this is so annoying. Okay. somewhere I've done this before. None of these though. Yeah, not in any of these. Sort by last updated. Great. I think I've got this in here though. Somewhere I've done this. Okay. It must be here. So in this project, I had a Nix shell. Haha! This is the one. I have this nasty set of flags. So when the shell starts, we run this code. Okay. And here, I probably had to add these here. Okay. So let's just close all this now and run this again. Oops. I forgot to semicolon here. Now, hopefully, if I run bind gen on the header, everything is happy, so just give it a sec. I have to download Clang from the internet so that I can run it on this header. Then I'll be able to use that to generate Rust bindings. Just give it a sec. Bump, 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 bump. Bump, 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 bump. Bump, 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 bump. Oh, sick. Ooh. Unlucky. I forgot to add this final thing here. Extra quote, close it off. Come on. Yeah, okay. So now I should be able to go into here, bind gen. Still no good, hey? Why did this work before for me? Oi, 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 oi. That sucks. Okay, I don't want to deal with this right now. That's frustrating. So I wonder, maybe for now, I'll just reference the multiboot header manually and convert it myself, because it's not that hard, right? So if I go back to this example, I have memory map is, I iterate over the memory map adder. So this is the multiboot info, the multiboot descriptor. So they're kind of claiming that here there is a contiguous chunk of memory that has several memory maps, and all I have to do is read them. So here I can, let's see if we can get something sane from here. So the memory map, the length of the memory mapped section is info add 44/4, and we're gonna call this. It would be nice if I didn't have to do all this like pointer casting. So let's first see if we can like construct this header, or sorry, this multiboot struct. So here we'll just pull in this guy, right? Oh, it's this guy here. We can pull this guy into main like this. And we can just go through the magic manually. So here, jeez. Oi, oi, oi. So this is a flags is a U32. Mem lower is a U32. So let's do this. We'll first start by moving these types around like this. We'll come back to this, right? Move these around, and then we'll search and replace the types to be what we want. And what I want to find here is I want to find out if the bootloader name, if I can get to the bootloader name in here, then I'm happy. Right? So let's close this off and convert multiboot uint32t to a u32. And now we just have to figure out how to allocate this. And so I think this is bytes 20 to 48. So I can just stub those out. So 40 minus 28 is 12. So this is just a, we'll call this dummy. And this is going to be just like a U8 for 12 bytes, right? And so now, hopefully, if I say ripper c packed, give me this layout directly, I should be able to print the bootloader name still from a, what do I call this thing? Multiboot info. So let's see. So this is bootloader name underscore. So bootloader name is like this. Like this. Like this. Info bootloader name. So let's open up my development environment. I don't know how I got out of it, but that's okay. We give it a second, get running, get warmed up. I need to dereference, obviously. Ugh. Okay. Sorry. Management of shells. Frustrating sometimes. Okay. So here we need to dereference that info somewhere, which was in main. Right, we have to go like this. It still is unhappy. What doesn't it like? Oh, source env. Okay, so nothing, which is not what we were seeing before. So we have to figure out why this is not at the right address. So this was supposed to be 64 bytes offset. And I think that in Rust, I can actually get the offset of, so I can do core offset of, I think it's called. Let's just give the internet a second to resolve. ST code core mem offset of container field. Yeah. So here I should be able to say core mem offset of multiboot info bootloader name. And I want to see the number 64 here. And if I don't, that's a problem. We can call this put U32 as U32. And it doesn't like that. Unstable library feature offset up. Okay, so let's just add that feature. And it just doesn't print anything. Okay. 60. So that's far off. We want 64. So let's just add another 8 there. 66. Oops. Obviously. Okay. So now let's see if this works again. Put a right name slice like this. Okay. Okay, so we now have got this correct. So the question is, why did this need to be 16 bytes instead of 12? Did I miss something here? Because let's just double check the multiboot spec. So this is 0, 4, 4, 12, or 4, 8, 12, 16, 20, 24, 28 plus 16. See, like, this seems wrong to me. This should be to 40. Oh, this should be to 44. Okay, okay, sweet. So all this lines up. Which means that now I can say, how many memory pages do I have? So what we were trying to get to is these two fields here. There's mmap length and mmap adder. This tells us like the memory ranges that we are allowed to access when we implement our pager. Which means that we can print the how many maps we have. So let's try that. Map length. So put u32 info and map length. 144. Okay. And now what we can do is we can try starting to iterate over those. So multiboot h. So here somewhere I had it open an example of them iterating over those chunks. Here. And so these are multiboot memory map T's. So I need to find these, and that's this, right? So here I just say multiboot mmap entry. And size is a U32, adder is a U64, len is a U64, and type is a U32. Okay. And these should be commas, not this. And I have to say that I want these not to, don't fuck up my memory layout, please. This goes away. Okay, so now I can cast these to mmap entries. So, let's say for in 0 to the mmap length, like this. Terminal writer. So now we need to get the multiboot mmap entry. So we say mmap adder info mmap adder plus 4 times I, because we have the size of a pointer, times I, which is 0 on the first iteration. We say that we need to access this as a, what is this thing called? Multiboot mmap entry. Right? And then we want to print size And then we want to put adder, and then we want to put a new line, right? And so the size will be a U32, which is star p len, I think it was called. Size. What is the difference between size and len? Interesting. What are those? How are these not the same thing? Where's the multiboot spec? Len. mmap star fields are valid, and the length of a buffer containing the memory map of the machine provided by the mmap adder, and the mmap length is the total size, but the buffer consists of one or more following size. Size is really used for skipping to the next pair. Oh, okay. So I don't actually care about that. And I actually want to put U64. And put U64 will be defined in terms of put U32. So I just put the first half, then the second half. So I say put U32 C shifted right by 32 bits. And then this, right? Okay, and we'll just put this as len, like this, and this would be adder. I think the adder was a U32. It is a UN64. Okay, but presumably the adder, how do I say this? Presumably it only takes up 32 bits. Okay. So let's see if that does anything. mmap adder needs to be dereference. What? Oh. This needs to be dereferenced here. I forgot some semicolons. And this needs to not use reserved keyword. Okay. We're close. Let's make sure that I got these right. So how can I have multiple items at the same address? Oh, I need to do the size of this struct. So this needs to be core mem size of multiboot mmap entry, like this. I think it's like this. Like this. Expected use size found U32. There we go. There we go. Nice, nice, nice. Okay, that's sick. So we've now found mmappable regions. Right? So we have, yeah. The addresses are like incrementing. I think that's sane. And I think that's enough for this stream. So this is kind of fun. We got to the point where we haven't actually done any implementation of paging, but at least now we have like a way to find what the pages are. We've like figured out how to like get arguments from multiboot into our kernel. We've also kind of like sorted out some like assembly mistakes. We know how to like push to the stack, which is like the most basic concept, but I was fucking it up. So we're now familiar with how to passed parameters from assembly to Rust. We've parsed the multiboot header. We haven't done it with like bindings, but we've done it with just like direct Rust implementations. And we've printed like our bootloader name, so we know that we're like parsing the multiboot input correctly. And next time we can start trying to use that information to try to generate actual paging logic. Generate's the wrong word. Implement. So thanks for tuning in. This has been fun. I'll catch you on the next one. Bye.